Hello, everyone. Welcome to another episode of Science and Technology Q&A for kids and others. And I see there are a bunch of questions that have come in here, and let's see how I can do with them. Let me see. Oh, boy. There's a question here from Blank asking, why are there both herbivores and carnivores? Isn't it evolutionarily best for everything to be omnivorous? So it's like, why are there creatures that eat only vegetables, creatures that eat only other creatures, other animals? Why shouldn't everything be set up like us humans are, where we have the capability to both eat meat and vegetable material? That's why we have both grinding teeth and pointy canine dog-like teeth and so on. I don't specifically know the answer. And one thing that tends to happen in these evolutionary explanations is that things developed in the way they developed in the course of biological evolution. Then we look at the answer, and then we come up with some explanation for why it had to be that way. And sometimes it's a bit of a put-up job, what answer one comes up with. But I would say the following thing in general, which is that if you want to be a creature that both, swims in the sea, flies in the air, waddles up mountains and things like that, you've got to have this whole collection of different kinds of apparatus to do that. And that's complicated to arrange. And it usually is the case that the more specialized the creature is, the more likely it is to be successful. And the way it shouldn't, if the creature adds a tail because that's a convenient thing to do for some very special thing that it does, but sometimes the tail gets stuck when it's doing something else, and the poor creature is killed because its tail got stuck and some other animal ate it or some such other thing. So, typically, having additional capabilities in the case of biological evolution tends to add sort of cost to a biological organism. Things can go wrong. If you have that extra little thing sticking out somewhere, it can get infected, or things can happen to it. And if you're just the sleek, simple, I just do what I do, and I'm specialized, and the thing I do works out, it's all good. Now, of course, the problem with where it's very specialized is if things change in the environment you're in or something like that, and the specialized thing you were doing no longer makes sense or no longer works out, then you're toast. And then the generalist organism tends to do better. I mean, the big sort of meta discovery of organisms was the ability to learn. That is, there was, and presumably many early organisms, sort of their capability to do what they did was determined genetically. The thing had these, these legs, and all it knew how to do with those legs was this. And then increasingly, organisms started to be able to learn during their lifetime. That is, even if they had this set of legs, which were sort of normally intended to do this, well, actually, the organism could learn that you could do something different with those legs. And so it was less fragile, less determined how it was going to work and what it was going to do based on purely on the way that it was sort of physiologically constructed. I would say that it's sort of interesting, this question about specialization versus generalization, and when specialization is the right strategy, when it isn't, depends a bit on the environment, depends on a bit on how changing the environment is. We can ask the same thing for technology, is when is it better to be special purpose versus general purpose? I think that, again, it depends on what you're trying to do. I mean, this is an issue we see. Let's talk about, for example, computers. There was a time before people understood about general purpose computers, before people understood about the idea of programming a computer to do different kinds of things, when people imagined that you had to have different hardware-built computers for different functions. And that turned out to be not such a great idea, because the idea of making a general purpose computer is an idea that has great economy of scale. That is, you just have to make that one kind of microprocessor, you make zillions of them, and you make them very, very efficient. And then for each particular function you want the computer to do, you just have to add software. Now, I suppose that one could think about this for brains as well. One can imagine, and in fact, this was certainly true of lower organisms, that there are special purpose brains that just do particular things. And then there are us humans that have, at least as far as we're concerned, fairly general purpose brains that we can kind of learn all sorts of different things with. And that turns out to be, at least in our ecological niche, a good idea. I mean, again, in this question about generalization versus specialization, one could certainly imagine a situation where having that, that big brain that can do all sorts of different kinds of things would actually be a negative for the survival of the species. It could be that the better thing to do is just have those species be pure drones that just do what they do and don't have them think too much, because if they think too much, they'll go off and do other random things and get themselves in trouble. I mean, sadly, there are certainly situations in human society where I think that tends to be the, just have the people do what you wanted them to do, so to speak, and don't have them think too much for themselves. I think that's an unfortunate place to be, but that's something that can happen. So in any case, I think I'm sort of diverging quite a bit from the original question about carnivores and herbivores, but I think this general point about when is it better to be specialized for a particular purpose, when is it better to have this capability of generalization, I think that's the trade-off one's talking about. And I think in many places in biological evolution, specialist wins, and it's but not all places. And it's an interesting question as what aspects of kind of the environment and so on affect whether the generalist will win or the specialist will win, so to speak. I think the history of life on Earth, insofar as we're the top species right now, the generalists seem to be winning, since that's kind of where we are in the chain of species, so to speak. All right, let's see. Let's see. Okay, this is a specific comment from Michael here about saying short digestive systems are better for meat as they offer some protection from infection, but are less efficient for extracting nutrients from plant matter. Fire allowed us to enjoy both worlds. That's interesting. It's an interesting point. Yeah, I can see that as being the case, that there are critters that, like I don't know, cows and things that have, the multi-stomach, let's take some grass and extract something from it, whereas the meat is all ready to be consumed, and the proteins are all ready to be taken. Okay, we have another comment here from Steve. Aren't we specialists in terms of our ability to think? Interesting. The thing that, okay, so there's a question of what kinds of things can one imagine happening in the world, so to speak. So if we believe that the world operates according to certain rules, certain natural laws, let's say, what kinds of things might be in those natural laws? And can we find a way to represent how well, what kinds of things can be in those natural laws? That's one sort of basis for how general are things. Well, one of the things that's come out of, for example, our physics project, and came out a bit from earlier work of mine, is this idea that the things that we now know that we can set up in computers, the kinds of operations that computers do, the kinds of things that a general purpose computer can do, seem to cover really well the kinds of things that our physical universe can do. So we could say, well, there might be other things that our physical universe can't do and our computers can't do. And those are things that indeed are not captured by things in our physical universe. But now we can ask, when we look at things that we do with our brains, to what extent can we successfully capture the things that are going on that are possible in principle in our universe, or possible in principle with computational systems? And I think at least at a theoretical level, that we are covering pretty well with our brains and with the kinds of operations that we can do with our brains. We are covering the general category of things you can do with computation. So for example, it is, although we may not be super fast at it, we can in principle follow through the kinds of operations that our physical world does to do what it does. The physical world is doing it much faster than our brains do it, but we're not like, oh my gosh, we can't conceptualize anything that's even vaguely like the way the physical world works. At least that's the impression we have. And so, this question of whether our brains are, so I think it's sort of a core basic level that the things we can do with our brains are the same as the kinds of computational things that can be done in the physical universe. Now, if you ask the question, can we do it easily or not? That's a whole different question. And the story of kind of the development of science and things like that has been to take kind of the raw material of what we can do with our brains and build these kind of stepping stones, these sort of towers that allow us to get to a higher level and then work from that level. So for example, when we invent mathematics and mathematical notation, we're inventing something which can be implemented in our kind of brain level hardware. But once we have the idea of mathematical notation, we've jumped much further. We've made use of sort of discoveries of humans. We've learned from that. And now we can sort of operate with our same sort of brain hardware. We can do more sophisticated things. I like to think that my kind of life work of developing computational language, finding a way to sort of represent the world in sort of computational terms, is providing us another level of kind of step up in terms of what we can operate with our brains. We can think in terms of computational language. If we've learned Wolfram language or whatever, you can start to think in terms of computational language, and you get to be able to conceptualize things that if you were just left kind of to the raw brain without any of that learning, you wouldn't be able to do. So there's sort of a question of, are there modes of thinking that we haven't yet encountered, which once we get that idea, we'll be able to start thinking about all sorts of things in all sorts of terrific ways. I would say the best example of that in the last 100 years or so is this idea of computation. Before, the notion of general purpose computation, the notion of, all the things that come with that, the sort of symbolic representation of the world, the idea of rules that operate on rules, and all sorts of things like this. Before those notions were known, it was very hard for people to think in those kinds of terms. And there was definitely a block in what could be conceptualized, what could be kind of imagined for purposes of science or purposes of kind of general intellectual rational thinking. So, as we move forward and we learn more and we sort of build this sort of taller tower of abstract concepts and so on, yes, we will start to be able to think in different kinds of ways. I mean, that's typically sort of the notion of a paradigm, the notion of a new way to think about things. That's all about having this kind of new domain in which you can kind of conceptualize new sorts of things. And if we look over the history of the development of science, for example, we see a variety of stages of kind of new conceptualizations of things. So, I think that the sequence that I've been sort of identifying in recent times is, back in antiquity, a couple of thousand years ago, the big question was, what's stuff made of? And I don't know who first started to ask that. Maybe nobody cared that, you look at these different things, the rocks, the plants, the ocean, whatever else. And maybe nobody had really cared, what is this made of? And is there some commonality in what these things are made of? Maybe nobody had really, they say, there's a plant, there's an animal, it does what it does. We don't really care what it's built up from. But people started asking that question, and people started thinking about things in terms of what their individual small component parts were, and often realizing that they were the same component parts repeated in many different kinds of systems. And that was, for a long time, that was sort of what the science or the early sort of pre-versions of science looked like. Then 1600s, the big sort of thing that came in was the idea of let's use mathematics to describe the natural world, write formulas for how things work in the world. That's another different level of thinking about things. And there were concepts introduced like things like energy and, well, that was a little bit later, but force, momentum, things like this, which become concepts that give you ways to think about the world that people hadn't really conceptualized before that. You know, I think in my own sort of lifetime, the big thing was sort of this idea of computation, and this, I mean, that fundamental idea goes back about 100 years, but sort of its application to thinking about the world in general, as opposed to just thinking about kind of mathematics, for example, that's a much more recent idea of more like 1980s type timescale of kind of conceptualizing things that way and starting to reason about the world in terms of computation. So I think that's kind of the sense in which we gradually get different places that we reach in terms of our ability to think about things, different paradigms for thinking about things. In recent times, for me, this whole multi-computational paradigm is sort of a yet a new way of thinking about things. And I don't doubt, and in fact, I think it's an inevitable feature of what we know about the fundamental computational structure of the world, that there will always be new abstract ways of thinking about things. There's never going to be an end to sort of ways to conceptualize lumps of knowledge. And one will always be able to sort of build more and more pieces of the tower. Now, the question for us humans is, we build that piece of the tower, we say, well, in principle now, we can understand this or that thing. It could be the case that we just don't care, that the nature of humans, what humans are interested in, human society, it's like, well, yes, in principle, you could study this area of abstract mathematical kinds of things, but actually just nobody cares about it. And it's something where, yes, you could study it, but we're not going to. And that's a complicated loop between what we humans want to do and care about doing and what is possible to do. I mean, I certainly know there are areas of science, ones I've been interested in, particularly one area is the area of ruleology. This question of kind of when you have a simple computational rule, what consequences does it have? And often the big discovery I made in the 1980s is that even with very simple rules, you can have very complicated behavior. And the question then is, so what? And the answer is, in some cases, well, the so what is, it's connected to things we see in nature, it's connected to things we want to build in technology, but there's a large class of cases where you put down a simple rule, it does a complicated thing, you look at it, you say, that's quite interesting, I think that's interesting, but it's not clear that that's yet a thing where lots of people think it's interesting. So it's something where you can, in principle, do it, and it's not yet a thing where people say, oh, yeah, that's a thing we should do. So, you know, that's kind of the loop that happens. There can be a way of thinking about things that is in principle possible, but nobody cares, at least not for 100 years, 200 years, whatever. And then suddenly there's a reason why human society starts saying, yes, we really, really care about that. You know, this is the way to make sort of customized art where every piece of art looks different every time we look at it or something, and that becomes a really important thing. And then suddenly, what was this kind of obscure sort of tendril of how one thinks about things becomes much more mainstream. Boy, you guys are asking, commenting about things about biology I don't know. Parmenides comments about, don't we have lower amounts of stomach acid than carnivores do? I do not know. Sounds reasonable to me. Let's see. Let me look at some other things here. The question here about robotics, asking what's holding back robotics? Why don't we have humanoid robots yet? You know, what often holds back robots is very mundane stuff. For example, one thing is purely you have joints, and our way of having actin filaments and our muscles and things like that, pretty efficient. Often one of the things, and I noticed this when I see humanoid robots, the thing you really got to look at is what comes out of the back of the robot. How thick is the wire? How much power is going into that robot to actually move its joints around and do the things it does? There's a lot of kind of, well, I wouldn't say smoke and mirrors, but there's a lot of kind of strange trickery that often goes on in humanoid robots. A lot of issues that have been difficult to resolve that are very kind of mundane, like just you need a lot of power to drive those joints. Or, you know, for example, for us humans, our legs go, you know, we have a locked state where our knees are locked. And it's hard to do the robot motion planning when you can get to that locked state. And so people, a common thing, I think this is less true now, but maybe 10 years ago, it tended to be the case. You'd see a humanoid robot and it would always be a little bit, its knees were always a little bit bent because it was too difficult to do the sort of motion planning of how do you get the robot to this location when you had that kind of locking possibility. I think that I think there are both practical aspects of kind of the you know, motors and actuators and how good they are and things like this. I think there's a different thing, which is it's kind of the trade-off that one often sees between technology and biology. You know, if your goal is to make a flying creature, people back 120 years ago, something like that, 100 and more than that now, 140 years ago, whatever, you know, were convinced that the way you would make something that would fly is to flap wings, because that's what they saw birds doing. But it turns out that when it comes to the materials and control systems that we readily have, flapping wings is a pretty bad idea. And there aren't airplanes that flap wings on purpose, so to speak. That's great for birds, bad for planes. So in the case of robotics, one of the questions is things which are biologically convenient, given the actual things we have of, you know, actin fibers and muscles and tendons and all this kind of thing. To what extent is that something that when we are building technological systems which don't have those same components, to what extent should we really be following exactly what the biology has done? Now, one of the things about humanoid robots that's tricky is that we've built an environment that's really pretty good for us bipeds of, you know, that are roughly, you know, a meter and a half tall or whatever else it is, and that have arms and have opposable thumbs and all kinds of things like this. We've built the world so that we can manipulate it well. So you can say, well, I want to make a robot that just has wheels and it has a you know, one kind of grabbing, you know, sort of scoop or something like this. And it's like, well, that's nice, but the world that we've built that's all around us is really optimized for us humans with our detailed sort of way of grabbing things and walking around and so on. And so that's kind of a big motivation to build humanoid type robots, is we get to leverage, we get to exist in the same sort of built environment that us humans have. And that's something, so that's a reason to go humanoid, so to speak, in the structure of robots, even if it's actually very awkward in terms of the materials that we have available in terms of building robots. You know, my own suspicion about robotics, which is that one of the issues is that we've tended to make robotics very special purpose. You know, I haven't been to a robotics trade show in maybe 5 years, maybe more. But it certainly used to be the case that you'd go to a big trade show about robotics, and you literally, there'd be an aisle about hands, there'd be an aisle about, you know, legs, there'd be each different part of a sort of robot, there would be different hardware, different devices, different structures that were being set up for those different sort of pieces of the robot. Now, with computers, that's not what we have. We have general purpose computers. We have computers where you have a particular computer, and then it's merely a matter of programming to get it to do all these different things. Now, with industrial robots, there's a little bit of this, you know, you have one big arm and you can program it in different ways to do different things. But we're not at the point with robots where you can have sort of a general purpose mobile walk around type robot that can be like programmed to do very different kinds of things. And I've often thought that the way forward is to construct a robot in a way it's very different from the way biology does it, to have something that consists of lots of identical components, and where you have some complicated thing where all those little components are shifting around relative to each other, and you have this kind of thing which is like a bunch of little sugar cubes or something, and they're all sliding relative to each other and changing the shape of the robot, so to speak. Years ago, I tried to build some of those kinds of things. It turned out to be difficult for very practical reasons about the difficulty of just getting enough force and enough ability to deliver power to things, to move stuff around. I actually think some of those issues have now somewhat been solved, and it might be time to look at general purpose robotics again. And probably there are some different mechanical ideas about how to do it. But the question is really, can you make a structure that is really a truly general purpose robot where it's all turned into software, where it's no longer, oh, we have to have a specific, are we going to have this kind of grabbing hand or that kind of grabbing hand, where it's purely, the structure is dynamically built sort of at runtime, at the time when the robot is doing its things, and it's all sort of determined by software. Now, having talked about determining things by software, there are plenty of problems in robotics that even with the software capabilities we have today, they're really hard. Like, a typical one is the picking problem. If you've got, let's say, it's a problem of great practical importance for, big online retailers and things where they've got a giant warehouse full of millions of kinds of things people want to buy, and those things are all different shapes. And it's like, can you pick them and put them in a box? And the answer is that's actually pretty hard. And notably, the things that people make are typically, if you're a manufacturer of a thing and that thing is unpickable up by a human, it's probably a bad thing. It's probably not a realistic, it's probably something that's not going to be convenient in the world. So probably you make things which are somehow pickable up by humans, but to make them also pickable up by robots is a different problem. And the problem of making a robot that will do a good job of doing sort of human-like picking up of things has proven to be very hard. And that's, both like how much force do you put? Do you crush the egg or do you not crush the egg? Does the thing kind of slide out of your hand? What do you do? Et cetera, et cetera, et cetera. This has turned out to be hard. So, there are issues like that that are already around. Let's see. Yeah, comments. I see comments about neural nets and learning algorithms finding approximate solutions to problems in robotics. Yeah, that's certainly the case. I mean, a very common issue in robotics is you want to, take your finger and touch your nose or whatever. You've got to figure out how to run those motors in your, in your arm to move your hand so that you bring your finger to your nose or whatever, if you're a robot with a nose. That problem of, I guess, inverse kinematics is a problem. Actually, people have done a lot of work with algebraic computation, a lot of things using our software technology to try and solve those problems by understanding the kind of equations of motion of things and being able to invert them and kind of solve for how do we get to this position. I think there's sort of a new generation of those kinds of capabilities which have been built using machine learning kinds of systems. I think a pretty common idea, I don't know how well it really works, is this sort of reinforcement learning idea where you're kind of, you see what happens in the world and you probe the world. You say, what if I put my hand here? Well, then you say this happens. Okay, that's feedback. Then then we sort of learn from that. Now, in the theory of control systems, there's been for many decades kind of a oh gosh, what is it called? Well, it's not feedback control. It's a more general version of that. That is the same kind of technology as reinforcement learning. In both cases, it's developed using somewhat the same internal technology. The big issue tends to be, what's your kind of model of the world? What's the model that you are trying to learn against that says how things work and that you're trying to tweak to actually get the system to do what you want? But yeah, I think that's I mean, you know, there is definitely progress being made. I would not say that it's sort of blowing everything out of the park, at least based on the things I've seen. A lot of kind of the problems of, I mean, there's definitely been progress made. For example, in machine vision, the dramatic progress a decade ago from really, it was very hard to recognize objects and to tell apart, you know, the 5,000 or 10,000 kinds of picturable nouns that we have in English. What is this thing that we are looking at? That with kind of, you know, this was one of the surprise discoveries of deep learning neural nets, was if you bash the thing hard enough and train it long enough, you can have it actually make the correct distinctions between 10,000 kinds of objects and recognize those sorts of things. But there's, you know, the progress on sort of more subtle issues is it's going, but it's definitely not, you know, it didn't just suddenly arrive and now it's all solved. Let's see. Comments here, questions here about bioelectricity, which is something I don't know much about. Well, I mean, I know tiny amounts about it. It's, you know, there's, in a sense, there's, when we grow, what are the signals that determine how tissues and organs and things grow? And some of those signals are known to be chemical signals, often quite small molecules that can diffuse through other pieces of tissue, and kind of their concentrations define sort of, should we grow in this direction or that? Sometimes there are more actual contact kinds of things of, oh, you hit another piece of tissue, don't grow anymore. And I think there's decent decent evidence that electrical processes can also affect kind of the way things grow. I think you know, the thing that I mean, one of the things about biology is a little bit like technology. It uses everything. So, you know, if there's a mechanism, you know, if there's some mechanism that involves using little atomic magnetic moments to sense magnetic fields, if there's a mechanism that involves using some optical effect in here or there, there's a good chance that somewhere biology will have used it. Just like there's a good chance that somewhere in technology, somebody will have used that effect once discovered, so to speak. Now, some things biology finds it hard to get access to, like there aren't a lot of wheels. There are occasional ones, you know, bacteria, you know, there are bacteria with flagella that kind of go round and that are sort of driven round like wheels and so on. But on large scales, you don't see a lot of wheeled animals and things. So there are things which, for one reason or another, biology has a bit of a hard time accessing. But generally, if there's a mechanism, biology will typically somewhere make use of it. And then the question is often, well, how important is the use that it makes? And that can be a feature, you know, when we ask about, I don't know, physiological, medical effects of things. It's like, well, you know, how important is our electromagnetic fields on affecting biological organisms? No doubt there is an effect. Is it an important effect? Is it an effect that's going to sort of, you know, kill us all off? Is it an effect that's going to make us all get smarter? Is it, you know, what's the, is it a significant effect? Is it not a significant effect? That's a much harder thing to assess. I think, let's see, there's a question here about, from Glitch, about thoughts about computer-designed organisms. Well, I mean, we don't yet have the capability to do that. I mean, what you know, we can create, you know, and it's increasingly straightforward to do gene editing, to edit the DNA of organisms and make a different organism by changing the DNA. Knowing what consequences that will have is really hard. I mean, we don't know. If you just show me a piece of DNA and say, what's this going to do? That's a difficult thing to figure out. The very first level of that is from the DNA, from the original base pair sequence on the DNA, one is defining the sequence of amino acids that will be used to construct a protein. One of the things that got significantly easier in the last few years is knowing, given that sequence of proteins, sequence of amino acids in a protein, let's say, 100,000 amino acids or something in a sequence, in a line, in a protein, that protein is going to curl itself up into some shape. And that shape is determined by the sequence of amino acids. And the question of exactly what shape is the protein going to wind up in is something that was very hard to figure out computationally. It's become in the last few years, it's through machine learning kinds of things and a lot of just ingestion of data from existing knowledge of how proteins get folded up. It's become much more straightforward to know how will the protein fold itself up. And it's important to know that because a lot of the operation of proteins in biology is associated with the actual physical fitting of one protein into another, or things like, I don't know, the hemoglobin in our blood. It's a protein that happens to have a little hole in the middle of the protein that's just the right size to fit an iron atom. And so our hemoglobin picks up iron atoms, and that's how we transport oxygen around through our blood. And that's just one example of a zillion mechanisms. Our muscles have triple helices, I guess, which are again proteins that can be extended and not under electrical effects. And I think the protein, the general idea, protein is a very flexible material for making things out of. It's what we're made out of, basically. And we can now, so the specification of make a protein, well, we can do that. The question then is, first question is, well, if you just write down a random DNA sequence, what kind of protein will that make? It's been something I've been curious about for a long time. If you just write random DNA sequences down, forget biological evolution, just pick proteins at random. What will they be like? Will they be useful? Will they not be useful? I don't think we really know. I think there is a certain sense in which probably, given a protein which is a certain shape, biology may find a use for that protein, more so than biology kind of scratching its head and saying, what shape of protein should I make? Now, there are places where making random proteins is done in biology. The immune system, the adaptive immune system, is all about making random proteins, basically. You're making in the antibodies, for example, we make 10 billion different kinds of antibodies that are made at random as little short sequences of protein, basically. And those different short sequences make the antibodies be different shapes. And those different shapes are shapes that will attach to different kinds of antigens, different kinds of things that might infect us, so to speak. So, we're kind of a little bit onto the make a random protein kind of idea. That's how the immune system works. But in terms of the technology of make a random protein and see how it be useful, that's not something we're doing at this point. And in terms of the designer protein idea of, let's kind of make something where we design the protein, where we specify the sequence to make a protein that's a certain shape, that's just becoming it. It's because of advances in sort of computationally determining the shapes of proteins. One's just starting to see serious work being done on, we've got this shape we want to achieve, now let's make a protein that forms into that shape. And I think we're in very, very early days of knowing what kinds of shapes will we care about. We could imagine making all sorts of micro machines that would do all sorts of interesting things out of proteins, but I don't think it's been well conceptualized what kinds of shapes of proteins one would like to make. And now, as of very recently, it becomes somewhat possible to see how one would construct such a protein. So in terms of sort of computer designed organisms, that's kind of, I think, the leading edge, and it's very recent leading edge of sort of the designer protein. Now, people tried 20, 30 years ago now with design of drugs. So drugs are often, sometimes they're small molecules, but sometimes they're proteins or bigger molecules. And when one wants to have a drug, the usual sort of workflow of developing a drug is a common kind of approach is to first find a target. That is, oh, we found out that if you get this kind of disease, this kind of thing happens in this type of cell, this type of receptor on some cell surface is modified in this way. Okay, that's a target. That's a thing we can go and do something about with a drug potentially. Then you have to actually design the drug that will hit that will attach to that target. And often that's a question of making a thing which has the right shape to bind to that particular thing, like puzzle pieces fitting together. And there was a big enthusiasm about 25 years ago, maybe now, for so-called rational drug design, of just like you make a computer-aided design system and you're like drawing your molecules and then we're going to make it this way. It didn't really pan out at the time. Maybe now it will become more possible again. And what tended to happen instead is that people would do the kind of much more empirical thing of saying, we've got this target. We know what we want the drug to do. Now we've got this library of 5 million substances that we got from all over the place. We found them from the bark of the tree in the Amazon jungle. We found them from this kind of insect. We've manufactured them in this way. Let's just try, a gazillion of those substances and just see if any of them actually are useful for this particular target. And that has been kind of that sort of combinatorial chemistry. Well, actually, there are ways to do that even in a more sort of structured way, not so much just trying the library, but actually constructing molecules. But that's been a sort of typical way to do things. Whether it's possible to actually sort of design from scratch, that looks now to be somewhat more realistic, only very recently, though. Now, when it comes to bigger things of, can we make an organism that will, I don't know, the famous example from science fiction, the movie Blade Runner, at least the original version of it. I think it opens with this scene of this character who is a biological designer, so to speak, who has all these little creatures that, one of them opens the door of his apartment. One of them, starts making coffee or something. And it's kind of a vision of biology as technology, so to speak. Actually, back in the 1970s, even, I remember people talking about, technology and electronics, they're never going to make it. What's really going to happen is biology, and one's going to be able to make sort of designer organisms, and they're going to be the way to make things happen. Mostly that's not how it's played out. There are a few exceptions. For example, when genetic engineering was first coming online in the 1970s, 1980s, one of the big things that started happening was the ability to kind of piggyback on top of things like E. coli, very common bacterium, and instead of having it make the proteins it usually makes, have it make the proteins you want it to make. And that became a very common way to make drugs. For example, insulin is often made that way, where you just have given an insulin gene to this bacterium, and you've got a giant vat of this bacterium, and but instead of it making the stuff that it normally makes to just be the bacterium, it's got this extra gene in it that is making a substance that is useful to us, a drug or a biological agent that's useful to us. So that's a case where we did sort of piggyback on biology. Now, of course, in times past, a lot of processes for making food and things have been, and other materials for that matter, have been, again, sort of piggybacked on biology. But that's a more direct version of that. But I don't think at the level of having an organism, a little creepy, crawly, ant-like thing or something, we're not there yet, not even close to being able to make, the designer ant that can, one might imagine a situation where instead of, sending the, where you could say, oh, we've got this problem, we need to clean up this mess that was made by something or other, nuclear reactor mess, or a mess made by some chemical spill or whatever else. Let's send in the artificial ants that have been designer created to be suitable to deal with that. We're not to the point where we can do that right now. we're still to the point where at best we can send in the robot, so to speak, with the right kind of apparatus to deal with it. Let's see. Question here from Lilb. Could we build robots out of random proteins? Good question. The problem is we don't really know how to do sort of engineering at a molecular scale. The only, we biological organisms are pretty good at doing engineering at a molecular scale. And, we have all these mechanisms of molecules interlocking with each other and doing things and so on. That's all happening at a very molecular scale. And we have managed to sort of orchestrate that. That's what we biological organisms managed to do. We don't know how to do that yet, technologically. We can make things, when we make things technologically, like a microprocessor. Microprocessors have, they're made by essentially photolithography. They're made by taking, a big chunk of silicon that's been made very pure. And then what you're essentially doing is taking a photograph of the whole pattern of wires that you want in your chip, and you're projecting that photograph down, using ultraviolet light and X-rays and all kinds of things like that, to a very, very tiny region in silicon. And you're just straight etching away the places where light falls or doesn't fall or whatever. And that's the way that you're making this kind of giant roadmap of where all the wires are going to go. It's very solid-based stuff. It's very much, you've got a solid thing, it's a crystal of silicon, and you're etching away the places where you want the wires to be, and that's how you make the giant kind of giant circuit that is going to be our microprocessor. And one nice feature of that is once you made it, it is that way. That's it. You etched it out. You get multiple layers of etching. You put different dopants in it and things, but it's just you're kind of making it as a solid kind of thing. In biology, we often at least think that that's not how things are working at all, that it's more liquid phase where there are a bunch of molecules, they're moving around, they're bumping into each other, they're arranging themselves in a particular orientation. That's how they're operating. I think it's becoming clearer that there are more features of biology that are more solid-like than we think. So for example, the cell membrane around every one of our cells, very similar to the lipid nanoparticle membrane that was used for the mRNA vaccines, for example. But that is essentially like a crystal. It's a single layer, but it's got a bunch of little molecules that are all arranged in a very rigid array. And when we look at the surface of a biological cell, it's basically that lipid bilayer thing of a bunch of these sort of rod-like molecules all stuck together in this hexagonal array, I think. And then there are things poking through that are all kinds of different sorts of essentially sensors and actuators on cells. There are molecules that sense things. There are molecules that deliver material. There are molecules that pull material in. There are all kinds of little tubes that transport proteins. A very common motif in a protein is what's an alpha helix, which is a place where the amino acids have got in a helical shape, and there's enough sort of a gap inside the helix that you can transport small things like ions, but things like sodium atoms and things like that through that alpha helix to transport them in and out of a cell, and that's a mechanism that biology uses a bunch. But biology is full of these kinds of mechanisms like that. And I think the challenge of making technology out of biological components is really the orchestration of all these different pieces. I think it's biology. A biological cell has got this rigid outside, more like, well, it's floppy, but it's locally rigid. It has all kinds of things sticking through it, and it's got all these mechanisms. And within a cell, it's increasingly clear that there are these little fibers that transport materials, and it's all pretty organized. It's all kind of very factory-like. It's much more factory-like than one might have thought. It's much less like a chemical plant because a typical chemical plant, things are operating in a liquid phase or a gas phase. Liquid phase is the sort of favorite phase to get chemical reactions to happen in, because in a gas, there are molecules bouncing around, but there just aren't that many molecules. And so they don't react that much. In a solid, the molecules are just locked in place, so they don't get to, if two molecules really needed to meet to have a chemical reaction, they probably won't meet because they're stuck in the solid far apart. But a liquid, things are sort of really moving around, and that's sort of the best place to get chemical reactions to happen. That's why, when it comes to, airport security and so on, it's like, don't take too much liquid, because liquid is what you need to make some nasty chemical reaction that one doesn't want. But if it's just solid, you can't do it in the same way. So it has been the case that one's thought, I would have thought, that a lot of what's going on in biology is liquid phase chemical processes, but I think that may not be really correct, and that it's more machine-based. It's sort of mechanoidal type stuff where you have these things that are like tiny pieces of more like solid things. And in fact, my own guess right now is that when it comes to sort of the bird versus plane kind of issue of, you want to make a thing that sort of has the advantages of biology, but is made with technological components, just like you want the advantage of biology of being able to fly through the air, but you want to make it out of technological components like aluminum rather than out of feathers and things. So, my own guess right now, very recent guess actually, is that the way to think about this is to imagine making things that are very much like microprocessor chips out of solid objects, but that have all sorts of tubes and wires, effectively, more so tubes, because if you're interested in actually doing things with molecules, you can imagine something. So in a microprocessor, what you're basically moving around is electricity. You're moving electrons around. And in those wires, you're arranging for the electrons to go, a voltage will push the electrons from one end of a wire to the other, and you're arranging to sort of herd the electrons around your microprocessor. So the thing that I'm kind of suspecting is that you can make kind of little tubes in your sort of generalized nanotech microprocessor that are capable not of having electrons herded through them, but having protons, for example, hydrogen nuclei, or having other kinds of molecules sort of herded through them, and that becomes something which is kind of the technological version of something like biology, in the sense it's making use of molecules, making use of chemical types of things, but it's doing that in a way that we can technologically control. Anyway, that's my current guess for how to think about that kind of thing, and I'm sort of it'd be quite wonderful if we could figure out how to make a collection of designer proteins. For example, here's an interesting exercise. We got something like Lego. We got these bricks. You can make all kinds of interesting things out of it. And this is a little bit related again to the general purpose robotics question of what kinds of primitive elements do you need to make an interesting physical device. But just going for the Lego thing for a moment, an interesting question is whether, with sort of modern approaches to sort of designing a protein of the shape you want, so to speak, whether you can actually construct something where you can make a good construction kit. People have tried to do this a little bit. I mean, there certainly have been some rhetoric around making sort of biological bricks, so to speak, but it hasn't, I think, gotten that far. And it ends up becoming sort of degenerating back down to essentially pure genetic engineering of, put this particular, gene that makes a particular protein into this particular organism. So the question, I think, really now is, if we can make a protein that's any shape, and by the way, it's not totally obvious we can make a protein that's any shape. That's another thing that will be interesting to figure out, is given the raw material of proteins, amino acids, whatever else, we know there are certain motifs that are pretty common, like alpha helices, like beta sheets, like other kinds of shapes. But is it in fact the case that protein stuff, amino acid sequences, how general are the shapes that those can make? What is the space of possible shapes they can make? It's probably quite broad. The antibodies make use of the breadth of those shapes, but I don't know to what extent, if you said I wanted to make I was going to say, I want to make an icosahedron, a 20-sided platonic solid, 20-faced platonic solid. And I was like, maybe that's hard. And I realized, no, that's what viral capsids are often that shape. That's actually something quite easy to make out of protein, it turns out. But so if you pick a shape, it's an interesting question. What shapes are easy and hard to make out of protein? I don't know the answer to that. And to what extent, if you were to make a construction kit where, for example, could you make things that really are like Lego bricks with little cylindrical things that fit onto other things? I don't know. I suspect the answer to that is you could make that. So that's a question of in terms of making things out of protein. But yeah, I think it's kind of an interesting idea to do that. I'm not to make proteins that are the right building block shapes to be able to build things up to appropriate size. Of course, then there's still the question, even if you've got those proteins, how do you actually get them to assemble to the right shape? Now, something like a crystal, the way a crystal grows is it's got that solid surface of very organized molecules that are arranged in the array that they're arranged in the crystal. And then there's maybe a liquid, molecules in a liquid floating around. And then whenever they hit the crystal in the right place, they'll stick on. And then the crystal will progressively grow, but they'll only stick in such a way as to be arranged in the correct grid to make to grow that perfect crystal, so to speak. And so the question then is, if you're trying to make sort of a more complicated kind of structure that isn't just a regular periodic crystal, how would you grow that? I've looked at that actually a bit. And this question of sort of what kinds of things can you grow by having essentially tiles that you lay down and which sort of arrange themselves just according to some matching rules for tiles. My guess is, and I know theoretically, that it's possible to sort of make more or less arbitrary patterns that way, but actually coming up with tiles that do that and coming up with proteins that would sort of naturally do it, and where the protein would, with reasonable probability, stick on in the right way and so on, that's something that is not yet to the point that we know how to do it. Damp is commenting about Eric Drexler's work, sort of the namer of nanotechnology, and person who in the 1980s did a whole bunch of work on thinking about how to make molecular scale machines. I think my feeling is that, well, unfortunately, that whole field, for reasons of essentially scientific politics, kind of crashed on the rocks, very unfortunately. I mean, but it's interesting to look at the kind of sort of the concept, some aspects of which I think were on the right track and some I'm not sure were so much on the right track. Kind of the idea was, let's take machinery, cogs, gears, levers, things like that. Let's take mechanical machinery and let's try to shrink it down to molecular scale. It's not obvious how you do that, because a lot of issues about forces and trade-offs between the strength of things and the force they can exert and so on are very different when you're molecular scale than when you're made out of giant pieces of steel or something. But that was a thing that Eric Drexler studied a lot, was what are the trade-offs when you really shrink things down? And the answers were pretty interesting. And I think the conclusion from that was, yes, you really can make shrunken pieces of machinery. Now, the next question is that really the best way to make functionality that you want out of molecules? Some of that machinery, in some cases in biology, we see machinery being used. There are molecular motors where you're turning a flagellum to make a bacterium swim, so to speak, things like that. There are things which look very, mechanical engineering machine-like in biology. There's also a lot that doesn't look that way. And so the question is, if you're trying to achieve certain functionality, is the right way to do it to go to the sort of the steam engine phase of human technological development, to go to the mechanical devices and look to sort of shrink those down to molecular scale? Or is the right thing to do to say, let's figure out what functionality we're trying to achieve, and then perhaps use other primitives which aren't the things that we know from gears and levers and so on, but are quite different shapes, quite different forms, quite different mechanisms, which happen to be convenient to implement with molecules. I have to say that my own work on kind of the ubiquity of universal computation, the fact that this idea I call the principle of computational equivalence, this idea that out of all kinds of stuff, you can make sophisticated computational devices. You can make it, you don't need to have the carefully designed microprocessor to be able to make something that computes. You can make computation out of all sorts of different raw materials. And that idea gives one the suggestion that perhaps you don't need to take what we already know on the scale of, levers and gears and so on, and shrink it down. That's not the only way to make useful functionality, useful technological functionality. Instead, you might just be able to take the stuff that naturally exists on a molecular scale and figure out how to essentially write software that will make that stuff operate in a way that does something useful for us. And I tend to favor that approach. Now, I have to say that I have been thinking in recent times that one really has to think through what does it mean to do a computation in liquid phase chemical reactions, things like that. I don't know completely the answer to that, although I do suspect that there have been some things where the usual way that we think about doing a computation, you ask a question, 2 + 2, what is it? Crunch, 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 we compute it. The answer is 4. I think when you've got molecules bouncing around in a liquid and the molecules are interacting in complicated ways, it's much less a molecules go in, crunch, 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 result comes out. There's a more complicated way in which sort of the computational process is represented. And my guess is that there's kind of a whole missing branch of chemistry that has to do with understanding not just how many of what kind of molecule come out in a chemical reaction, but more what is the kind of whole dance that individual molecules take on. Molecule A meets molecule B, then they go off and they meet other molecules. Later on, that very molecule meets that other molecule again. But having had different environmental experiences, so to speak, that's not something that's accounted for in chemistry. In chemistry, normally you're just saying there's this number of such and such a kind of molecule, this number of that kind of molecule. Every molecule of a given kind is sort of the same as every other molecule of that kind. It's not like each one has a sort of personal name and has had a sort of personal history in the chemical reaction. I think what we see in biology and molecular biology may make much more use of, every molecule has had its own personal history, so to speak, and it matters which individual molecule it is. That's something which at the scale that we usually operate in chemistry and chemical engineering and so on, absolutely invisible to us. At the scale that we usually operate, we're just dealing with big vats of chemicals and so on, or even if it's much smaller than that, it's still, trillions of molecules and so on, not the individual story of a particular molecule. Now, of course, those individual stories can aggregate up, and 1 trillion molecules can be having those individual stories, but it can matter that they have particular stories, and it isn't just a question of how many molecules do this or that. So I think I think there is ultimately immense promise to making a sort of molecular scale technology. In a sense, chemistry has been our approach to molecular scale technology in the past, but I think it's a very coarse approach relative to what's possible. I think that if you say, well, what's the use of molecular scale technology? One thing is you probably can do things faster, smaller, better, cheaper, lower power, all this kind of thing by shrinking things down and, just having a few atoms do that rather than having a giant, arm made of 1 trillion atoms doing it. But I think probably the thing for us, selfish humans, so to speak, that's probably the most important, is that because we are made from molecular scale technology effectively, or molecular scale biology, the interface to us is going to be conveniently done with molecular scale machinery. That is, if we want to do something where we say we want to replace some particular piece of some organ, or we want to do something that interfaces with some parts of brains or hearts or livers or whatever else, it's going to be something where we really need to go down to that molecular scale and have the ability to make machinery on a molecular scale to be a good fit to interface with us. I mean, we could say, we could imagine making technology where, technology has to be made so that humans can actually use it. That's sort of what the point of technology is. I mean, we could imagine a technology where it just, interesting things happen in these liquids that are floating around, but, humans can't control what goes on. And so it's not very useful to us. Let's see, maybe one or two more questions here, and then I should wrap up. Let's see. This comment about nanotechnology was talking about universal assemblers. We just mentioned what those are and why that's interesting. The question is, could you make any molecule? Could you just say, I'm going to type in some code, and I'm going to have all these arms moving around, these little tiny molecular scale tips and so on, and I'm just going to make a molecule? And we know how to do that for proteins. We know how to do that when the components are amino acids, these fairly, collections of tens of atoms and so on that are amino acids, and we're sort of connecting them together in a line. We know how to make essentially any molecule that can be made of amino acids. But now we can ask the question, can you make any molecule made of anything? And people were very interested for a while in making molecules just out of carbon atoms. And people tried to make, I think one of the achievements was a molecule called dogosine, which was kind of a carbon atom, carbon atoms arranged sort of in the shape of an idealized dog. I think, and then when buckyballs were discovered, a particular sort of the soccer ball configuration of carbon atoms, that was an example of one of these kinds of weird shapes made of carbon atoms. But it's a question, could you make a machine that would just churn out different structures made from carbon atoms? What's happened in practice is there were, what was originally known was diamond and graphite are two sort of forms of carbon, but then buckyballs were discovered, which is this actually exists even in soot, but it wasn't recognized there. These different sort of cage shapes, then graphene, which is kind of like a tiny tube made from the kind of thing that makes graphite, but it's rolled up in a tube, or sheets of that, things like this. Those are kind of different shapes of made from carbon atoms. And some of those things, like graphene, is very strong, has good electrical conductivity properties, things like that. So that's an interesting kind of material to make things out of. But you can also ask the question, could you just make an arbitrary thing with an arbitrary shape just out of carbon atoms? Nobody knows how to do that right now. The only ways we have to make shapes like that are through chemical reactions. So essentially what we're doing is we have kind of like if you had trying to make something, but you just had components that were really very big. You didn't get to ever have that little finger that's poking at something, that little micro manipulation thing that's just moving the one piece around. Instead, you've got this great big sort of robot hand or something that has to sort of bash at things and hope that the little piece that was supposed to go into that little hole will successfully be pushed into the little hole when you're bashing it with this really big, unwieldy hand. And chemistry, in a sense, is that kind of story. You've got a limited set of things you can do. You've got these molecules, they're floating around like in a liquid. You say this molecule will attach in this place. It's a pretty common thing to say, I want this particular piece of this molecule to attach in this particular way. In order to make that happen, I'll add a protecting group that will prevent the other part of the molecule from being affected when I affect the other part of the molecule. And then at the right moment in the chemical reaction, I'll do something which will pull off the protecting group. And then it'll sort of expose this thing, which I can then operate on in this way. It's a very challenging thing to do chemical synthesis. And it's designing chemical synthesis is an art form. And it's something where the typical modern chemical synthesis is maybe 25, maybe 30 steps long. And longer than that is really not doable yet. But it's a very much a coarse kind of thing where you're bashing at chemicals in this way and that way to try and get specific things to happen. So the question of, can you make a thing that's the shape of a rhinoceros or something, a molecule the shape of a rhinoceros, that way? And the answer is it's going to be really hard. You've got to have this piece which is bashing with a big molecule that's going to sort of try and carve out the horn. You've got this thing that's going to carve out the little tail, and it's really hard to do. So kind of the concept would be, could you make a universal assembler which just has this thing where it's like a little tiny tip, for example, that's just going around and knitting, it's just sort of drawing this rhinoceros molecule and just constructing it explicitly like that. So that might seem like it's crazy and very science fiction-like, but actually an atomic force microscope does do that on a very small scale. It can like pick up individual atoms and do things with them, but it can't do that on sort of on the scale you need for this. And the thing that has been believed for 40, 50 years now is that one day, actually even longer than that, even John von Neumann was talking about things a bit like this, although not so specifically with molecules, back in the late 1940s, early 1950s. This idea of, can we make a universal assembler where we just program it, and then that little tip moves around and it says, okay, I'm going to put a carbon atom here. Oh, I'm going to go back to my supply of silicon atoms and I'm going to pick up a silicon atom and put it here. It's kind of like, I'll just make a designer thing. It's kind of like in science fiction, you know, it's not uncommon to have sort of the universal constructor type thing where, you know, you press the button and it just creates for you the you know, mashed potatoes from nothing or something, just by taking the raw material of the atoms, you know, a bunch of carbon atoms and oxygen atoms and nitrogen atoms and so on, and just sort of makes that. And it's kind of interesting that when you look at you know, making a protein, for example, or making you know, a piece of DNA, you literally do have bottles of the different kinds of bases, the 4 different kinds of bases, for example, and you're combining them to make a piece of DNA of a certain kind. So we're almost to that point, but we're not quite to that point, and nobody knows how to make the mechanics of a universal assembler. And it's a thing where one might imagine that one day one will make a universal assembler, and then one can make anything. And in particular, the universal assembler can make more universal assemblers. And so once you have just one universal assembler, you can kind of make more universal assemblers in its image. Now, of course, we've seen that story before, because that's what life has done. Life made a living organism, and then living organisms reproduced themselves and made more living organisms. So in a sense, the idea of the universal assembler that makes universal assemblers is a repeat of the idea of life. That's sort of an ultimate sort of holy grail objective of nanotechnology. You know, a thing people got kind of worried about is, if you can make anything, then you can make things that are, you could, for example, turn everything into some kind of gray goo that would just be sort of some molecular soup that you could just sort of transform all matter arbitrarily into whatever you want, and things could go wrong, and you could turn all matter on Earth, for example, into something that isn't the way you want it to be. I think that that concern is probably a bit overstated. I mean, although we can plainly see that, you know, molecular scale, you know, the fact that we have a molecule that's, well, we have a virus that's got much more than just a molecule, you know, and we have, you know, the total amount of COVID virus is, you know, I think you still hold it in your hands. It's a tiny amount of virus that got spread around the Earth, and that when binding to all sorts of pieces of us, caused all kinds of trouble. So it's not the case that you can't cause trouble with molecules. There's plenty of ways you can, even with fairly small amounts of molecules, you can cause all kinds of trouble. But I suspect that the everything turns into this kind of goo is perhaps an overstated issue. Let's see. Oh my. Well, I think maybe one more thing, and then I should stop. And there's a lot of questions here about physics and computation, and I'm very happy to talk about that. I was off on a different topic here today. Ark asks, what if every microorganism is also a macroorganism? What is a macroorganism? Well, I suppose I don't quite know what a macroorganism is, other than something that is big and has lots of cells in it. And typically when people talk about microorganisms, they're typically talking about single cell organisms and so on. I think that it is an interesting question. When does, for us, we are solidly built out of trillions of cells. For, a colony of bacteria, the cells are all separate and they're all floating around separately. But nevertheless, there can be communication between those cells and so on. And it's not totally obvious the extent to which, when is an organism, what is the boundary of the organism, so to speak, as opposed to, the ant colony. There's all the individual ants, but they are doing things in a coherent way where they're communicating using chemical signals and all sorts of things like that. And, you could ask about human society. To what extent are the 8 billion of us or something doing something coherent where we are operating as a sort of macroorganism and so on? And yes, it's an interesting question when, it's a feature of biology and actually a feature of the world in general that, well, okay, so it seems that there is sort of modular layers where, there are organelles inside a cell, there are cells, there are organs made of cells, there are, collections of organs that make an organism, there are collections of organisms that make, a whole herd of organisms, there are a whole species, et cetera, et cetera, et cetera. There are these different levels of organization. And it is an interesting question to what extent, when we see levels of organization, to what extent those are in the eye of the beholder, to what extent we are identifying those, and to what extent we can really make sharp distinctions about those different levels. When we build technology and engineering, it's very common to want to have things be modular in the sense, and why is that useful? It's typically useful because you can say, I'm going to build this module. I'm going to have, put a lot of effort into building this module, and then I don't have to worry about how that module works inside. I can just plug it together with these other modules, and then together I'll make something that works well. And so, biology is presumably doing the same kind of thing. It says, I'm going to make a kidney or something, and it's going to work in whatever way it works, but you can just assume it will filter blood, and that's its large-scale function. You don't have to sort of worry about what's happening inside, and you can kind of, operate organisms on the basis of kind of just taking that as a modular piece. But so I don't know, the extent to which I kind of imagine this kind of notion of the bacterial army, so to speak, and to what extent the thing can operate in a coherent way. I think we generally assume in microbiology that, I think it's generally assumed that, if you get infected with something, some microorganism, some bacterium, let's say, that every bacterium is fighting for itself, that it isn't the case that the bacteria, in your gut, for example, they interact by virtue of the chemicals one bacteria produces that will affect another bacterium, et cetera, et cetera, et cetera. But I don't think one's imagining that there's some whole signaling mechanism where the bacteria are, sending little radio signals or something to each other to all decide, oh, let's all go do this thing. To my knowledge, there's no mechanism known for things like that. I mean, well, having said that, there are certainly small molecules that can get produced by one microorganism that will affect other ones. But I don't think, this concept of, let's command the whole army to do something, I don't think that's generally viewed to be what there aren't mechanisms for seeing how that happens. Whereas in a full organism like us, there are mechanisms by which our different cells, which are typically arranged in this fairly rigid way, do manage to communicate and do manage to operate in these sort of coherent ways to get us to do sort of the seemingly coherent things that we tend to do. All right, well, lots of interesting questions. Thank you very much for all of that. We should probably wrap up for today. Yeah, great. Well, thanks for all of that, and see you another time. Bye for now.